Rp is a more relevant energy function. And now Gibbs free energy and Helmholtz free energy. They involve a few more variables, and we can say the following, that if the energy is supplied to it under the condition of constant temperature and volume, then that goes into increasing the Helmholtz free energy. Or if the energy is supplied to it under the condition of constant temperature and pressure, then that goes into increasing the Gibbs free energy. Okay? So we're sort of trying to make a little sense of these energy functions that we had come across. You remember that these are not variables which will be directly visible to us, and therefore we will find it necessary to include them. They basically came out as a result of various possibilities in which all the variables, thermodynamic variables, can be put together. So Helmholtz free energy and Gibbs free energy were of course proposed by Helmholtz and Gibbs. And they are useful energies, as they call them. And I'll also have a small exercise to show why they are called useful energies. Let me first of all take this very basic understanding of the Helmholtz free energy from one of the most basic equations or inequalities that we wrote in earlier classes. Clausius inequality told us that over a closed cycle, dq by t is less than or equal to 0. This is the statement of Clausius inequality. And we also saw that integral a to b dq by t is less than or equal to SB minus SA. Okay, delta S is greater than or equal to dq by t, delta q by t. And delta q by t would be integral of dq by t from a to b, and that will be delta S. Okay, so let's say we do the following. We say that this statement actually amounts to saying that 1 over t times q that takes us from system A to state A to state B, which is either heat being given or heat being taken, is less than or equal to SB minus SA. Okay, which amounts to actually saying that QAB, A to B, is less than or equal to T times SB minus T times SA. Okay. Now what I can do is, but I would like to do is to add to the two sides WAB. So I'm saying QA to B, amount of energy supplied to the system, plus the amount of work that is done on the system, is less than or equal to this quantity TSB minus TSA plus WA to B. Alright, so I could write DQ, I could write DW, I could write DW over here, but I'm just writing this as DQ and this quantity. Alright. this I know that this quantity is equal to du, and du is equal to ub minus ua, right? Q plus w, dq plus dw is equal to du, and du is ub minus ua, and therefore this statement is that ub minus ua is less than or equal to the quantity on the right hand side plus w a to b. And then I will take TSB minus TSA onto the other side, and I will have UB minus TSB minus UA minus TSA is less than or equal to WA to B. The statement therefore is that this is FB, Helmholtz free energy of the state B, minus FA, Helmholtz free energy of the system A, is less than or equal to WA to B. So when work is done on the system in taking it from state A to state B, then it causes some change in the free energy of the system, Helmholtz free energy of the system. But that difference in the Helmholtz free energy of the system is still not equal to this unless the process is completely reversible. It is less than the amount of work that was done on the system, if the process is the usual irreversible process. Okay, normal process. Let me repeat. I will say this again. So the change in the free energy that the system has acquired as a result of the work that was done on the system is less than the amount of work done on the system. Some energy was lost somewhere. Okay? So that energy was lost somewhere. Where was it lost? And I will describe that. But this energy is therefore the useful energy stored by the system. System stored some energy, but that energy which then it can use to do some further work is less than the amount of work that was done in the first place to create this energy. All right? So what this inequality describes is the natural loss of energy that happens in physical processes. Energy is lost somewhere. Okay? These losses are the losses which we encountered in the second law of thermodynamics. In saying that you can go this way but you cannot go this way, that somehow the energies are lost. That statement is given over here, and the free energy therefore over here is the stored energy, which is the usefully available energy after you have discounted the system losses. Okay? And that system loss is something that I will also describe over here. I have it said in a slightly different form over here. We said F is equal to U minus Ts. So I have dF equal to du minus T times ds minus S times dt. And if I say that, look, this process is taking place at constant temperature, so I put a bracket and a T outside, then this will be equal to this du at constant T minus T times ds. The last term will be 0 because this is being done at constant T. And All right? And I can then say, what if it is also being done at constant volume, not only constant temperature but constant volume, then this is equal to du at constant temperature and volume minus TdS at constant temperature and volume. Let us try and read out the meaning of this statement. We notice that this is, when we said that, made that statement over there, QV goes all into U, we said this is the, when we work under the condition of constant temperature and volume, then whatever energy we supply from outside will all go into increasing the internal energy of the system. So this is the amount of energy that was received by the system.
So when the energy is constant, should du not also be equal to
No, that is for ideal gases, okay? Don't confuse there. du is a very complicated thing. The expression that you have in your mind, 3 by 2 nRT, is for ideal gases only. Okay, this question was, when if dt is equal to 0, shouldn't du be also equal to 0? That is true for ideal gases only. Okay. So this is when you keep, this is the energy that was supplied to the system. We all know that because this is what we said. Under the condition of constant volume, whatever energy you supply to the system goes all into increasing its internal energy. So this is the energy supplied to the system, and the energy which is stored is this minus this energy. And this energy is the unavailable energy. This is the energy, lost energy, unavailable energy. Unavailable energy means that this energy, this is equal to the energy that goes into increasing the entropy of the system. Okay? So this goes into changing the entropy of the system. And therefore this is something which is lost. And free energy is that energy which was received, but then if it wants to use it again, it will have to discount the energy which is lost. I can make a similar exercise. I think this explains the physical significance of this energy function. I will make a similar exercise for the Helmholtz free energy G. G is equal to U minus Ts plus PV, and therefore you say this is equal to H plus H minus Ts. H is U plus PV, you all remember, and therefore dG is Th minus Tds minus S dt. And then I apply the same condition. I will say, okay, what if I were to take it at constant temperature? Then this will go away. And then I say, what if I do it also at constant pressure? And then I have again the same interpretation, that all the energy that comes in under constant pressure goes into increasing the enthalpy of the system. So this change in enthalpy under the condition of constant temperature and pressure describes the energy coming into the system. And that energy that is coming into the system is degraded by this energy, lost. And that what is left is this energy, which is the useful energy. Useful energy under the condition of constant temperature and pressure. All right? So this is the significance of Gibbs and Helmholtz free energies. Any questions at this point? Yes?
Use the exactly
Useful energy, what do I mean by the term useful energy? Useful energy is if I store some energy and I want to use it at some other point, then what is left of it is the useful energy. So if it is more like, if you have earned some money and have it in your pocket, but then your pocket has some hole in it and some money is sort of drops down somewhere, then what is left is the useful money that you have. Okay? So this is not, this is the energy that has gone into the working of the thermodynamic system.
So can you please give us the idea about how in real cases the du actually not zero in the case of constant temperature and volume?
Now you will have to say that again.
I was saying that can you give us the idea or example that how the du is not zero in the case of real gases when we are keeping temperature and volume constant in the case of Hermit's free energy?
Okay, the question is, can you give us physical examples to show that while in the case of ideal gases, internal energy change is zero under isothermal conditions? This is not the case in the case of non-ideal gases. This is the question, right? Okay, so, we can do that easily. In fact, it can be, maybe one of the examples that I take today will describe that. Or maybe we can conjure up an example and show this. Show this, okay? Any other questions? Okay, so now my task is to familiarize you with all the horrendous looking algebra that we did in the last lecture. Okay? Although to many of you it was not so horrendous looking, but to some of you it was. And I think the more we take out the mystery out of them, the better it is. So what I will do is I will go through some exercises and examples, and you have some of them before you right here. And what we will do is we will take up those examples. And this one more thing before I move on. Actually, this was reminded by Amna, Kaniz Amna. The one thing that I didn't quite mention in my talk in my lecture, the last lecture, in describing Maxwell's relations, I had taken, for example, and I will try and show you that you can take any ratio derivative and try and make a Maxwell relation out of it. So I will ask you to give any derivative. dpvts ds by dt. No, ds by dt is not enter in the, ds by dp. So ds by dp, and as soon as you write ds by dp, then you say that it has to be at constant temperature, right? Because s is here, constant here, and because this is a s and p in the same bracket, so a minus sign, and because of p there is v over here, and because of this s there is t over here, and because of this v there is p over here. So as soon as you think of a particular derivative, you can write down the Maxwell relation. One of the Maxwell relations is this. Okay? All right. Suppose I had not this, but ds by dp at constant v. Right? At constant, not at constant t. As we said, in Maxwell's relations, s, there has to, the constant quantity has to be the conjugate of the quantity in the numerator, right? Suppose we had this, then what happens? And this can be easily seen in the following way. Because this is a derivative, I can take an inverse of this, and the whole thing will be just the inverse of this quantity, right? As I said, derivative, you can just invert the derivative, so I can write it this way. Now I can write a Maxwell equivalent of this. Now I can write a Maxwell equivalent of this, and I can say that this is equal to minus because of PS minus, and because of this S I can have T, I will have T, because of this P I will have V over here, and because of this T I will have S over here, and inverse of this, which is equal to minus dV by dt at constant S. So this was not among the 4 relations that you wrote in the last one, ds by dp at constant V equal to dV by dt at constant S. It was not a part of this, but then if you just invert both of them, I will invert both of them, and I'll say this is dp by ds at constant V. Oh, sorry, there's a minus sign, and is equal to minus, I've taken minus on the side, dt by dV at constant S is exactly the relationship that is a part of this. This was a part of your relations that you had derived earlier. Okay? So if you come across something like this, you would know that you only have to invert it to be able to get the Maxwell equivalent of it. All right? And today we will actually do several examples, the ones that are shown in this sheet of paper that is circulating now, and try and use the algebra to work through various things. Is it okay? Right? Fine. It all makes sense, right? And sort of it makes sense so clearly that you can start from any of this ratio and then work through it, and all the equivalents are worked out very easily, nicely. So the sooner we overcome this mystery, the better. This was a point to be made over here, and then I come to these questions that we have before us, and we need to go through them and try and solve them. Many of the questions have the word ideal gas in them because we know that there is this ideal gas equation. We will use ideal gas equation to work through them. I have not included any real gas, otherwise that particular question would have been answered. But let's see. A gas is allowed to expand adiabatically from an initial volume and temperature V1 T1 to V2 T2. Find the final temperature in terms of the initial temperature and see if that has caused an increase in temperature or a decrease in temperature. Okay? So let us see if adiabatic expansion, which allows volume to increase, causes cooling or heating. Okay? This is what we need to find out. The thing to do is that we want to look at change in temperature as a change in volume takes place, and this will take place if we write this as dt equal to partial derivative of t with respect to v, and the condition is that it has to be adiabatic. Okay? So I wrote this expression. Is that a simple? Is that an expression that you can easily follow? No? Okay. Let me write it in different form. I say, which I actually omitted the first 2 or 3 steps, and then it will become very easy for you to see. If I take temperature as a function of volume and entropy. Why volume and entropy? Because these are the two variables given over there. Adiabatic is when heat cannot enter or leave. The sole representative of the variable heat is entropy for us now in the algebra that we are doing, right? Entropy, we have pressure, volume, temperature, entropy. So entropy is the sole representative of heat. So whenever we say heat is neither entering or leaving, we say, okay, ds is equal to 0. So S is constant.
Sir, we know the entropy of the system is increasing because the uncertainty of deposition is increasing.
So there are other sources to increase in entropy. But we are talking of heat not entering and therefore entropy remaining constant. Okay? So at least that is not the source of any increase in entropy. So entropy remaining constant. That is what we say. And therefore we say dt is equal to partial differential of t with respect to v at constant s. And I would like you to add the second part of this statement. Plus dV आएगा, yes, you're right, good, plus
Partial S. Sorry, partial D by partial S.
okay, partial derivative of t with respect to s at constant volume times ds. Okay, so this is the statement that we have over here, and then we say if it is it is isentropic, as you said, adiabatic. And adiabatic means no change in entropy. Then this part is 0, ds is 0. What is left is exactly what I wrote over there. Okay? So that therefore becomes clear where this thing has come from. And we basically say if parameter A is changing with respect to when parameter B is changed, if parameter A is changing because parameter B is changing because of this, then we write the relationship of this as this under some condition. So under that condition. Alright? It is as simple as that. This is what I wrote over here. Anybody who is not happy with this statement? Everybody knows, yes.
Can you explain again why did you omit that term?
Oh, I said because this is the question says adiabatically. Adiabatically means entropy doesn't change. So ds equal to 0. So this vanishes. And we are left with only this part, which is what I had in here. Okay?
आपने temperature को function of D and S लिया है.
Right? Oh, why? Okay, good. The question that he's asking is, why did you take temperature a function of volume and entropy? How did you think of it? Why didn't you take it a function of pressure and number, for example? The answer lies in the question that is before you, which says that temperature, you want to find change in temperature. For what? Change in temperature under the condition of a change in volume in adiabatic conditions. So you have volume as the other parameter, and adiabatic condition means entropy is the third parameter. Okay? And the third variable. And because of that, you have therefore this a very natural way to look at things. Alright? Or you can also look at it this way, just forget about that and say, look, you're looking at change in temperature when there is a change in volume, and this can occur with this kind of strength of or whatever, the process that goes with it. The process will be given by this partial differential. Any other question? All right. So now we are set to work through this. Okay. Now we are set to work through this, and we need to calculate dt by dv at constant s. Anybody who can suggest how to go about it? What do you suggest we should do to get some meaning out of it? And what is the purpose? The purpose is at the end we would like to have all this described in terms of response functions, in terms of heat capacities, coefficient of thermal expansion, compressibility, and so on and so forth. So what do we do? Yeah?
Constant pressure.
Constant pressure. How would that enter into it?
So then you have alpha P.
Oh, if I were to make it into a constant P, then there would be an alpha P coming in. Right, correct. But then we have the condition is not constant pressure, it is constant entropy. You will have to think of ways of bringing in pressure over here. And that will not be easy. You want to include, who is saying that? You are saying that. Maxwell relation. So he is saying use Maxwell relation. So let us say the Maxwell equivalent of this is dP by ds at constant volume, and then a minus sign. Then what do you do with it? Then what do you do with it? Yeah? Anybody can think of, okay, let me go back, let me also help you with another thing. I think we should have in front of us some of the mathematical tools. We have already used this partial differential of x with respect to y at constant z is partial differential of y with respect to x at constant z inverse. एक तो ये है, फिर partial differential of x with respect to y at constant z is given by partial differential of x with respect to t, another variable t, at constant z divided by partial differential of y with respect to t at constant z. I am writing down those expressions which I wrote yesterday, but which should be in front of us so that we can know what mathematical manipulation we need to do. So this is the second relationship, and the third relationship is derived from the cyclic rule, and that reminds me of telling you something else also, which I will do that in a minute. This is equal to minus partial differential of z with respect to y at constant x divided by partial differential of z with respect to x at constant y. Okay, you will need a few minutes to write down this thing. Few seconds. And be sure that you are accurate, you know. Constant वाली term किसी और जगह न लगाना, और this is very important, what is being differentiated with respect to what and what is being held constant. All of that is very important. So if you're copying this relationship, be sure. And this is also equal to, you can also express the same derivative in the form of minus partial differential of x with respect to z at constant y divided by partial differential of y with respect to z at constant x. Okay, both of these come from the cyclic rule. And I am reminded, knowing the cyclic rule, expressing the cyclic rule, I am reminded of one question that I received very insistently after the last lecture. When some of you came and said that, look, partial differentiation means that everything else is held constant. If partial differentiation means everything else is held constant, then why are you writing a partial this variable as the constant variable outside the bracket? Everything else is held constant. Many of you came and said that, when you write dV by dt at constant p, well, partial differential, p should be constant. So why do you write p constant outside? And similarly with the others. And I sort of argued with them that, look, there are so many variables. Many of them are held constant. Many of them are irrelevant. And therefore they are not mentioned over there. But actually a relationship of this kind, where you have this cyclic relationship, gives the answer to that question. How does it give the answer to that question? Because if I do not put any constant outside, assuming that constant is already taken care of, and I take this out, then I actually am in a condition where I can cross y with y and z with z and x with x, and I end up with 1 being equal to -1. Right? So your question was correct, but then you see, expressing even in differential algebra, even in the algebra of partial differentials, it is important that you describe what is being held constant. Okay? Otherwise, this relationship would not have been expressed the way it is expressed. Okay? So that perhaps answers the question, and I am going back now to solving the problem. Here we are. We should keep these in mind, and now I need suggestions for solving this term. By now you may have already thought of it, that a clever way of solving this thing. This wouldn't take us very far. So, any suggestions? Okay. So let me see. You see, the constants. The other thing that we should keep in front of us. Alpha p is partial differential of 1 over v times partial differential of v with respect to p at constant temperature. With respect to T at constant pressure, and kappa T is -1 over V partial differential of V with respect to P at constant temperature, and we can also have isentropic, and therefore S over here, and then heat capacity is Cp is T partial differential of H with respect to T at constant P, and V if this is Cv when V is held constant. So these variables should be before us also in trying to solve this thing. And I see that only under a very specific condition is S held constant among all these variables, when there is dV by dP. If that is the case, maybe we should do something to take S into the numerator. Okay? So we should take entropy over here. I'm erasing this now. We should try and take it S into the numerator. How do we do that? This is the way. If Z is constant over here, then this particular expression takes Z to the numerator. Okay? So I will now do that over here. Apply this relationship to this thing, and this will become, with a minus sign here, and partial differential of S with respect to V at constant T divided by partial differential of S with respect to T at constant V. Alright? The denominator comes out very clearly in this particular form. So denominator is very clear. Numerator is still not very clear. Somebody is asking a question.
Why did we do this again?
Why did we do this? The reason was, as I said, among all of these response functions, entropy is held constant only in the definition of Ks. That is when V and P are different. We have differential of V and P with respect to each other. And that was not the case over here. So we thought of taking entropy into the numerator. Okay? That will help us get somewhere. Yeah? Any other comment or question? No? So move on. What do we do now? So we have ds over partial differential of SO with respect to V at constant t. What do we do with it? You want to apply Maxwell relation again? So Maxwell relation is equal to dP by dt at constant V. Right? So what? You're still nowhere near any of these. Sorry?
जो रिलेशन पहले लगाया वही बाहर क्या था
dp upon dv
dP upon dV
and dv upon dt.
We can't do that. There's V being held constant over there. Alright, what he suggested was that we take this and write this as dP over introduce an intermediate variable V and write this as this. We can't do that. Sorry, dP over dV and dt over dV. No, I can't do that. We are dividing by V and we can't take V constant. This will be indeterminate. This will be undefined.
dv over dp divided by dv over dt.
Okay, so you want to, he says that we should do the following. He says we should take dV over dP at constant V divided by dV over dt at constant V. Again, you're saying you should take 0 by 0. Okay? This is not the way to do it. Not allowed. So, okay, let us do something else. Let us introduce, go back to ds over dv at constant t and introduce the parameter which has been left out. Try and introduce that parameter inside and make it ds over dp at constant t divided by dv over dp at constant t. Allowed, right? This is allowed, okay? Right? And here I can then, this is no minus sign over here. I have only added a variable in between, pressure. And here I now change this into its Maxwell equivalent, which is minus dV by dt at constant p, and down here I have dV by dP at constant t. Correct? And because of this, I now can use this dV by dt at constant p is V times alpha p in the numerator, and dV by dP at constant t is minus V times kt in the denominator. So I have therefore minus V alpha p and minus V kappa t, and therefore this is equal to alpha p over kappa t. All right? Is someone not happy with this? Is it clear to everybody? Right? What I did was I introduced an intermediate variable p over here, and then I converted this into its Maxwell equivalent, which was easy. P For P, V, there is V, and for S, there is T, and for V, there is P over here, and because of S and P, there is a negative sign over here, and this remains as it is, and then I could easily see that dV by dt at constant P is V times alpha P, and dV by dP at constant T is minus V times kT, and that is what it is. Alright, so here we have this quantity. Let us stash it away and go to the next quantity. Yes? I'm sorry? I'm sorry?
Is there any systematic way to go about this, or do we just...
This is so unsystematic, right? I'm going so unsystematically, right?
Algorithm से उसका कुछ नहीं समझ आ रही।
क्या हुआ?
कोई एक procedure, step procedure type नहीं समझ आ रहा।
अच्छा, मैं बड़ा खुश था कि मैं प्रोसीजर सिखा रहा हूँ। मैं बड़ा खुश कि मैं प्रोसीजर सिखा रहा हूँ। मालूम हुआ कि मैं तो प्रोसीजर सिखा ही नहीं रहा। I see. So what to do? I'm trying to make it as systematic as it can be made. And you can stop me where you think I have not been very clear. All right. The point is that, like in any other mathematical exercise, there will come a point where you will have 3 or 4 choices. And in choosing which way to go requires, number 1, a little bit of pondering over the thing, and number 2, some practice. These are the only two things required. And what we are doing is actually trying to take you step by step, showing that in all of this there are reasons to follow. So the previous work, in which we just went into some areas which were not allowed, were basically where we initially thought, or some of you thought, we should go, found out that was cul-de-sac, was closed street. So we came back, and then we followed. And the last hunch which I used is something which you should always keep in mind. There were 2 things that I have said so far which you should keep in mind. Number 1, whenever, and please pay attention, this is very important, whenever entropy appears as a constant outside here, use the formula which can take it up to the numerator. Okay? Just do that, because that will help you. And whenever you have entered into something which is not making any sense, introduce the 4th variable into it. You have 3 variables always in a given, so introduce the 4th variable and try and see if you can make sense out of it. And maybe you will again end up into a dark alley and closed street, but then you will come back and you will learn. And slowly you will go through all, and I'm going through this exercise in detail only for the reason to let you know that this is not something for which there is a set procedure and you will follow B after A and C after B and so on and so forth. No, you will have to, like in any mathematical exercise, you will have to be innovative, you will have to be clever, you will have to do all the manipulations cleverly. Okay? This is the best I can do. All right?
Sir, आपने जो cyclical rule लगाया है, इसके अंदर जो variables constant है, वो तीनों different ही होने चाहिए।
I actually, I use this relationship. This one. And cyclical rule was what I had written and then erased from here. And then from cyclical rule, you can actually derive either this relationship or this equal to this. All right? So, is there any problem with that?
Sir, जिससे आपने T तीनों T लिखे।
कहाँ पे? यहाँ की बात कर रहे हैं? यहाँ पे साइक्लिकल रूल नहीं लगाया मैंने आपसे कहा था प्लीज पे अटेंशन। मैंने यहाँ पे साइक्लिकल रूल नहीं लगाया, यहाँ पे मैंने एक वेरिएबल दरमियान में ऐड किया, जैसे मैंने यहाँ किया था ये वाला, एक और वेरिएबल मैंने दरमियान में ऐड किया। ओके?
सर आप दोनों इक्वेशन में आपने फिट कैसे कराई, इसके बाद वो कैसे लिखा आपने?
दिस ये कैसे लिखा, इसकी बात कर रहे हैं आप? ये तो इसका मैक्सवेल इक्विवेलेंट है और ये वैसे के वैसे है।
सर एक और बात कि पी और पी तो कॉन्जुगेट आपस में एक ही तरह।
और नहीं तो इस वजह से ये तो मैक्सवेल रिलेशन में नहीं है ना, ये तो यहाँ से तो हमारे पास निकल आया पूरा रिस्पांस फंक्शन dv by dp एट कांस्टेंट t, रिस्पांस फंक्शन पूरा का पूरा निकल आया, ठीक है ना। अब बाकी मान रहा आप लोग अपने टीएस को परेशान करें, हैं, उनसे ज़रा खूब काम करवाएं ज़रा बार बार। तो दिस इज अल्फा पी ओवर kappa t. All right, we still have this ds by dt, and it is easy to see that ds by dt at constant v is cv over t, right? Do I have your attention? Okay, so this is ds by dt at constant v is cv over t, and this is cv over t, and therefore this expression dt over dv at constant s will be equal to this minus sign here, and ds by dv happens to be alpha p over kappa t, and then in the denominator we have cv over t, so we have cv here and t here. Okay, and therefore going back to the original question, we said change in temperature is equal to minus T alpha P over kappa T times CV times TV. All right. Now here you can, is it okay? मैं ऑब्सक्योर तो नहीं यहाँ पे, बिल्कुल क्लियर है हर चीज। All right. Here now, what you can do is you can take these constants to be constant. You can take alpha p, kappa t, and cv. Take alpha p, kappa t, and cv constant in the range of temperature that you have with you. One important statement that I should make, which I think you should always keep in mind, all these response functions are positive definite quantities. They cannot be negative. They are written in such a manner, including the negative sign, that otherwise, that these response functions are always positive definite. They cannot be negative. And therefore, you have over here, क्या हो गया? Over here, you have dt over t equal to minus alpha p kappa t cv times dv, and you can integrate them from v2 to v1 and t2 to t1. All right? And if you do this integration, जी T1 से T2 तक, sorry, T1 से T2 तक, yes. All right. So the first integral. Quiet, please. All right. तो फिर तो ये इतना गलत नहीं था. All right. So we can then take this as log of t, from log of t between t1 and t2 is equal to minus alpha P over kappa T Cp Cv. Please बातें खत्म करें ना. What is the problem? मुश्किल है तो हाथ खड़ा करें, सवाल पूछें. मुझे जी बोर्ड वो आप छोड़ दे, उसका पीछा छोड़ दे बोर्ड के हैं. ओके, ऑलराइट. सो log T1 to T2 is equal to minus, you want to see this board in full, minus alpha P over kappa T Cv times V2 minus V1, and therefore this is log of T2 over T1 equal to all of this, and therefore T2 is equal to minus T2 is equal to T1 times exponential of minus alpha P over kappa T Cv V2 minus V1. Now the interesting point over here is that if it is an expansion, then this quantity is positive. Then because all the response functions are positive, this is exponential of a negative quantity. An exponential of a negative quantity is less than 1. This is 0, less than 1. Exponentials come in like this and then go this way. Okay? So this is at 0, exponential is equal to 1, and below 0 it is when x is negative, this is x, this is exponential of x. When x is negative, this is less than 1. Okay? And then it remains less than 1 until it goes to 0 at infinity. Alright? So this is less than 1, and therefore T1 is being multiplied by a quantity less than 1, and therefore T2 is less than T1. This was being asked in the question. So what we are saying is that under this condition of adiabatic expansion because V2 is larger than V1, adiabatic expansion, adiabatic when S is held constant, expansion because V2 is larger than V1, the final temperature is smaller than initial temperature, therefore a cooling has taken place. So adiabatic expansion amounts to cooling. So this is what we showed over here. Alright. Next question. The next question is specifically about ideal gas. One interesting thing about ideal gas is, which I could ask you to do the calculation yourself, but then let us do it together. For in ideal gases, alpha P equal to, as we say, alpha P is equal to 1 over V times dV by dt when pressure is held constant. And ideal gas equation is PV equal to nRT. Okay, so dV by dt, so V is equal to nRT over P dV by dt when pressure is held constant is equal to this 1 over V outside, and this is nR over P, and this is equal to 1 over T. Right, unless it is specified that this is an ideal gas, it will be taken to be a non-ideal gas. So for ideal gas, alpha P is equal to 1 over T. and kappa T is minus 1 over V dV by dP at constant temperature, and this is equal to minus 1 over V dV by dP at constant temperature is minus nRT over P squared. Okay? And nRT over V is equal to P, so P and P cancels out, one of this P minus minus cancel out, and this is equal to 1 over P. So for ideal gas, the coefficient of the compressibility, isothermal compressibility, is 1 over P. You can't make a similar statement for adiabatic compressibility, which is the other compressibility constant. And for ideal gases, you have already seen that heat capacity, difference between two heat capacities is R. Cp minus Cv is R. All right? So this is one important thing that we should keep in mind in doing the next problem. Let me take it from here. का बड़ा डिस्टर्ब हो रखा है. All right, the next question. Okay, next question. बातें खत्म होंगी आपकी तो अगला सवाल शुरू होगा. All right? An ideal gas is compressed adiabatically by increasing pressure on it from P1 to P2. Find the change in temperature. Slightly different from the previous question, because here the temperature is changing because of pressure and adiabatically again. We could again start by taking T as a function of entropy and pressure, and again conclude that dt is partial derivative of temperature with respect to entropy at constant P plus partial derivative times ds plus partial differential of temperature with respect to P at constant entropy times dP. S0 नहीं कहा था, TS0 है. नहीं, चेंज इन एंट्रोपी जीरो है. एंट्रोपी के ऊपर डिपेंडेंस से मुराद ये कि यस एंट्रोपी इज बीइंग हेल्ड कांस्टेंट. यू आर राइट. तो एंट्रोपी वाज हेल्ड कांस्टेंट. यस.
हमने जब P चेंज कर रहे हैं तो वॉल्यूम भी चेंज होगा, तो हमने यहाँ पे V की डिपेंडेंसी क्यों नहीं लिखी P के अंदर?
इसमें हमने V की डिपेंडेंस क्यों नहीं लिखी? We could write that, but that would be an irrelevant term, because what is given in the question and what setup you are going to establish in your lab is going to change only according to the condition you say. You say that you will make it adiabatic, so that no heat, completely insulating, no heat enters or leave, and that you will keep the inside pressure constant. This is what you will do. Okay? You can always make a piston and let that piston slide. So you have therefore a cylinder in which you make a piston, and this piston then can slide inside to keep the pressure inside constant. And then this can expand or contract, change in volume, and there will be change in temperature. So there will be change in volume, there will be change in temperature, but we are only concerned with change in temperature, and therefore we will write only change in temperature. Under the condition that no heat comes in, no heat goes out. Okay? So in that case, this term vanishes, and you have therefore the relationship dt is equal to partial differential of T with respect to P at constant S times dP. Now, I will invite you to suggest ways to solve it. Okay, so the first recommendation is take S upstairs. So dt by dP at constant S is equal to minus ds by dP at constant T divided by ds by dt at constant P. All right? All right? This is, I have used this expression over here. And ds by dP at constant T is again something that we know. This is minus dV by dt at constant pressure by the Maxwell transformation. Maxwell equivalent of that expression is equal to this. Right? There is this minus sign, and then because of this S and P there is a minus sign, and P gives you, asks you to put V here and T here and P here. And then down below you have Cp divided by temperature. It is a simpler thing, and therefore you have this quantity given by the one minus and minus cancel out, V alpha P divided T times V alpha P divided by Cp. Okay? And therefore you will say that dt, now you will also then, because it is ideal gas, you will say that alpha P is equal to 1 over T. Alright? So alpha P is equal to 1 over T, and therefore T and T cancel out, and you will have dt by, I'm going to write it over here now, dt is equal to, on that side, V over Cp times dP. Is everybody happy with this? Stuff looks very simple, straightforward. I have used the fact that alpha P is 1 over T, so T and T cancel out, and I now have this. And because it says it is an ideal gas, so there is a P dependence hidden in volume. So we will use that. V is equal to nRT over P. So dP over P. Alright? But because of this, we now have generated another T over here. And if you want to integrate the expression, we have to put all T on one side and all P on the other side. So we have to take this T on the other side over here, and that this will be the expression. N is constant, R is constant, and Cp is taken to be constant. T cancel नहीं हुआ, उसको हमने यहाँ transfer किया. Or the other one, because alpha P is equal to 1 over T. Ideal gas. This is an ideal gas. Okay? So we have therefore from here, let me then erase these things. Done. We don't need this. So what we have is integral dt over T from T1 to T2 equal to nR over Cp times dP over P. Right? And this is integral P1 to P2. So you have log of T2 over T1 is equal to NR over Cp times log of P2 over P1. Okay? And I can write this as log of T2 over T1 equal to log of P2 over P1 to the power NR over Cp. And therefore T2 over T1 is equal to, or T2 is equal to T1 times P2 over P1 to the power NR over Cp. Right?
Find the change in temperature. So T2 minus T1 का expression है.
Okay, if you want to find change in temperature, T2 minus T1, you have T2 given by this, and T2 minus T1 you will have to work out. Okay? So what comes out before you is final temperature T2 in this form. Alright? Fine. So I am sort of taking you slowly, step by step, in a very unmethodical way. Sorry about being unmethodical. I will do these exercises also. Now, tell me, do you feel confident that you can do the remaining 3 exercises? I should have anticipated that you will say no. Why should you say yes? There is no reason. Okay.